Assalamualaikum. I am MEKG5163 ID M1125200019. Today I present a presentation. My presentation topic is HVDC system design and simulation for asynchronous AC network. Here we can see the objectives. The main objectives of our experiment are design an HVDC interconnection system, evaluate transmission efficiency and losses, analyze voltage, current and power transfer, static convert performance, verify system performance using MATLAB Simulink. So we have two AC network working at different frequency and voltage levels which cannot be directly synchronized. So we are going to use HVDC technology to provide a power transfer between these two networks. Our main objectives: design HVDC system interconnection and analyze voltage, current and power transfer along the circuit, evaluate transmission efficiency and losses as well, study convert performance and verify system performance using MATLAB. We can see here types of HVDC systems. There are three kind of HVDC system. One is monopolar HVDC, second bipolar HVDC, third homopolar HVDC. The types of HVDC that are commonly known, these three. The first one is monopolar HVDC, use single capacitor with earth or metallic return. Bipolar HVDC, which uses two capacitors with opposite polarities, and third type is homopolar HVDC, two conductors of the same polarity which with the earth on metallic return. In this experiment we are going to use bipolar HVDC for our system, which consists of 6 volts bridge configuration for both converter and inverter. This means 6 thyristor for capacitor rectifier and other 6 thyristor for inverter. They open and close in sequence from 1 to 6 with a 60-degree phase shift between each opening and closing. After adjusting the fire angle alpha 1 and alpha 2, our control system mathematically understands and regulates the voltage to mention a transfer power of 100 megawatt. We can see here also the rectifier internal configuration is first here and inverter internal configuration is here. We can see here rectifier, DC link, inverter, transformer, filter, smoothing reactors and power support. Our designing system consists of essential HVDC components, and inverter converts DC to AC. Other grid transmission provides voltage matching and isolation. We also implement some filters to reduce harmonics, which is generated by converter, something reactor to minimize ripples, and shunt capacitor to provide voltage support, and other reactive power devices. Here we can see our main simulation. Here we can see 3-phase VI measurement, 3-phase AC source, rectifier is here and oscilloscope is here, fire plus gen controller subsystem is here. Our 3-phase VI measurement is indicated here, inverter is here, and finally AC 3-phase AC source is here. Our designing system is mainly here. The simulation produces the clear concept, implemented the 10 steps. One is to create two asynchronous three-phase AC supply sources, two converters and inverter with the parameters of the resistor and their configuration, connected DC transmission link between the converter and the inverter, filters, use smoothing the reaction and capacitors, add necessary parameters, oscilloscopes to see the graph and the wave. We can see here the three-phase output wave from x-axis and y-axis. X-axis is for time, y-axis for voltage. This continuous, balanced and symmetrical wave form indicates that the system has acid stability, confirming that the firing angle are stable for efficient power transmission. We can say that we integrated a closed loop control system that automatically adjusts firing angle to successfully maintain state power. Here, as if from the simulation process that we have implemented by MATLAB, increasing the receiving in voltage and the current, effect of receiving voltage. We can see here two tables. After receiving two tables of results, the case on effect of receiving an voltage when Rx was fixed at 10 ohm and V2 was increased from 150 kilovolt to 300 kilovolt and alpha decreases and alpha 2 increases. This shows that the rectifier and be adjusted their firing angles to maintain the required power transfer balance the two AC networks. However, effective line resistance when V2 was fixed at 300 kilovolt and Rx was variable or changed 10 to 15. The transmission losses increase the higher line resistance. A large voltage drop was observed across the DC lane. However, alpha 1 and alpha 2 has not changed or showed very little change, indicating the convert operation remains stable. We notice when we increase the line resistance Rx, our closed loop control system reduced the DC current. This was not just stabilize power but also to maintain a safe extension angle, which is known as gamma at the inverter. By doing it, the system automatically shows that inverter communication failure. It provides that our controls design ensure stability under harsh grid conditions. Conclusion. Here we can see the conclusion. In the conclusion, we can say that the high voltage DC system successfully interconnected a synchronous AC network with the different frequency and voltage. Stable power transfer of approximately 100 megawatt was achieved from the simulation process that we have implemented by MATLAB, increasing the receiving in voltage V2, transmission current and associated losses, which is known as I square R. The high line resistance increased both power losses and voltage drop across the DC link. The converter stations mention stable and control power transfer under different operating conditions by adjusting their fire angle. Recommendation: we can see here the recommendation invested higher power rating and transfer levels. Effect of different settings on convert performance. Compare this to VSC HVDC system. Combine HVDC with reliable energy and thus can be implemented with the higher or more appropriate software. So in conclusion, we can see this study highlights the importance of consistent effort in achieving meaningful results. So thank you for your kind attention.